Welcome back to my course Aspects of Biochemical Engineering. Now, in the last lecture, I tried to explain that the heterogeneous reaction kinetics, and I told you when we immobilize the enzyme on the solid matrix, and since your substrate remain in the liquid phase, so it is an example of the heterogeneous system. And the heterogeneous system, the major problem that we face, that is the diffusion problem. And also we have reactions. Then the substrate has to diffuse from the bulk to the surface of the solid matrix, then and only then it will react with the enzyme and give the product, and product has to diffuse from the substrate on the surface of the solid matrix to the bulk of the liquid. So, you know that diffusion problem is there. So, there are two type of diffusion we came across. One is called external mass transfer problem, another is the internal mass transfer problem. Now, external mass transfer problem means when we assume the enzymes are immobilized on the surface of the solid matrix. So, it is not going inside the solid matrix. So, just at the surface of the solid matrix, how we can explain that particular situation, and we have come across the steady state condition where rate of mass transfer equal to rate of reactions, and we try to find out the correlation between damp Coulomb number and effectiveness factor. Damp Coulomb number, I told you, it is the ratio between the maximum velocity of reaction divided by maximum rate of mass transfer, and the effectiveness factor is the rate of reaction, the actual rate of reaction divided by rate of reaction when there is no mass transfer limitation. So, then in case of interparticular diffusion problem, that we have come across that when a particle present inside the pore, how that can be explained. We have come across the effectiveness factor and diethyl modulus, and we try to find out under what circumstances again it follows, it tends to the homogeneous reaction when eta value equal to 0, that is effectiveness factor is 0, how Thai modulus that plays important role in the interparticular diffusion problems. Now, this particular lecture we try to solve some numerical problems and to have the better idea on the immobilized enzyme system. The first thing that I want to show you that this first problem is the baby hamster kidney cell was immobilized in alginate bed. I told you the alginate bed that in the previous lectures, how the alginate bed formation take place. We know the sodium alginate, that is the soluble material. Now, what we can do, we can this cell we can make a suspension in the sodium alginate. Then drop by drop, if you put in the calcium chloride solution, then alginate bed formation is there. Then what will happen? Your cells will entrap inside the solid matrix that you can have. So, this is exactly what here the baby hamster kidney cell are immobilized in the alginate bed. The average particle diameter is 5 millimeter. The particle diameter means the size of the particle. This is equal to what we call it, this is equal to 5 millimeter. Okay. The rate of oxygen consumption at the bulk concentration, this is 8 into 10 to the power minus 3 kg per oxygen per cubic meter is this. This is the bulk concentration, and this is the consumption rate. This is per unit time what is the consumption rate. The effective diffusivity of oxygen in the bed is 1.8 into 10 to the power minus 9 meter square per second. Assume that oxygen concentration at the surface of the catalyst is equal to the bulk concentration. The oxygen uptake follows the zero order kinetics. So, then you have to find out are the internal mass transfer effect is significant. So, this is purely a mass transfer related problem, and this is the heterogeneous system. So, let us see how we can solve it. So, to access the internal mass transfer, we already know the observable Thai modulus. This equation we have already seen. This is the Thai modulus. Thai modulus equal to r square is the diameter. This is the and the by 3 whole square. The minus over that is the here the previously we told about the rate of reaction. This is the rate of oxygen transfer. That is the observed, and this is the diffusivity, and this is the substrate concentration. Now, in this problem, if you look at the previously that what is R? Question is that what is R? What is R is this is the average particle diameter is about 5 millimeter. Am I right? Now, if it is 5 millimeter, then how you can 5 millimeter? How you can write? You can write about this is 5 into 10 to the power minus 3 meters. What is meter? 1 meter is how much? 1 meter is equal to 100 centimeter. Am I right? And what is the millimeter? This is 100,000, 1000 millimeter. Am I right? So, that is why it is 10 to the power minus 3. So, this is the radius. Radius will be what? Divided by 2. So, it has come like this. Now, if you put this value, all values are there, that is equal to 3.88. Now, what we have observed that in the table, that in the last lecture I have shown you, that if the Thai modulus is more than 3, then it is mass transfer limitation problem that we have in the system. So, that is exactly we have written from Weiss criteria that if phi is greater than 3, the internal mass transfer effect is significant. So, this problem is very simple, only whatever data is there we just put in this equation, then try to find out the Thai modulus, and if you find out Thai modulus, from that we can speculate whether what is the if it is less than 3, then we may think little bit different. 0.3, then it may be mass transfer problem will be less, then reaction problem will be there. But since it is more than 3, it clearly indicates this is mass transfer, the limitation problem will be significant. Now, let me go to the second problem. Second problem is what? Second problem is the enzyme is immobilized in 8 millimeter diameter agarose bit, and at a concentration of 0.018 kg protein per cubic meter gel. 10 bits are immersed in the well mixed solution containing 3.2 into 10 to the power minus 3 kg per cubic meter of substrate. So, this is the substrate concentration that we have. The effective diffusivity of the substrate in agarose gel is 2.8 into 10 to the power minus 9 square meter per second. The kinetics of the enzyme can be approximated by the first order with the specific rate of constant of 3.11 into 10 to the power 5 second inverse per kg protein. Deduce the type of limiting region, that whether it is a mass transfer limiting region or it is a reaction rate of reaction controlling, that we shall have to find out from this particular data, that we shall have to calculate. Now what is given here? This is here the R, the size of the particle is given. This is 8 millimeter. Am I right? This is the diameter of the bit. 8 millimeter means the radius will be, again I showed you before also how it is millimeter can be converted into meter, then it will be 4 into 10 to the power minus 3. What is the diffusivity that we have? Here diffusivity is given here. Am I right? So, we can write diffusivity. In the absence of external mass transfer, the SB will be SB equal to SB is what is the substrate concentration that we have this is the substrate concentration 3.2 into 10 to the power minus 3 kg per cubic meter. Now, volume of the bit, how we can calculate the volume of the bit? We know the size, because we have already reported the size is 4 into 10 to the radius is 4 into 10 to the power minus 3 meter. Am I right? Then volume of the is 4 by 3 pi r cubed. So this is exactly, this is the, we consider this the spherical particle. So if we consider spherical particle, we can find out easily the volume of this. And there and 10 bits we have taken into consideration. So if you multiply by 10, it will be 2.68 into 10 to the power minus 6 cubic meter. The amount of enzyme present is the how much is there? This is 2 point this is the per cubic meter. This is the concentration of the enzyme. So if you multiply that, we will get the how much kg of enzyme present. The the rate constant, if you look at, the rate constant is what? That that in this kinetics of the approximate the specific rate is 3.11 into 10 to the power 5 per second per kg protein. So we calculated the amount of protein. In this problem, we calculate the amount of protein. So you have to multiply this amount of protein that is present there. Then we get the K value, and K value is coming about that 0.015 second inverse. And what is the kinetics of this? This follows the first order kinetics. This K into SB. Now, again we know that phi modulus is this, that the phi equal to Vp by Ap square into minus Rs observed DES into SB. Now, if you put these values here, how much values we are getting? The 12.69. Now, 12.69 the wise criteria that we have, if phi value is more than 3, the diffusion limiting region is there. So, it is very clear that this problem is diffusion controlling, because this is not reaction controlling. So this problem also, like in the previous problem, we can conclude this is also that mass transfer controlling. Now, this is the one problem that we have. Now, let me explain this problem. The problem is like this, because I told you that that one of the major application of the immobilized enzyme system in the Western country is the high fructose corn syrup. High fructose corn syrup production. So what we do here, as we know, corn, what is content? It contains starchy material. Am I right? Starch. So when it undergoes the saccharification process, this produces glucose. Now this glucose, when we pass through this immobilized column, this is the immobilized column. What is content? The immobilized glucose isomerase enzyme. Glucose isomerase. So this is so you are passing glucose here, and you are producing fructose. Am I right? This is how it is produced. So this is used for the production of high fructose corn syrup. And high fructose corn syrup largely used in the confectionery industry in the Western country. Largely it is used that as a sweetening agent in the Western country. Our country we don't use much, but the Western country is a lot of applications that we have. Now this problem, this related with this problem, that particular issue, if you pass this glucose solution in this column and convert it to fructose, now question comes that what for a desired conversion, what is the should be the height of the column. This is how we can design. How we can design the column, that what should be the height, this, the different height you have to find out, that what size is there in the column. So this problem is very interesting, so you try to understand. So what is here, that you see that the glucose is converted to fructose by using immobilized glucose isomerase enzyme. This you can correct it. This is that isomerase enzyme. The find out the height of the immobilized enzyme column. Following data are given. The diameter of the column is, so when you say that this column, so this column, the diameter, this diameter is about 5 centimeter. Am I right? 5 centimeter. The particle size is 30 to 40 mess. What do you mean by 30 to 40 mess? Mess means what? Mess approximately, the 30 mess means approximately, not exactly, approximately this is the pore size should be 1 by 30 inch. Now 40 mess means is approximately 1 by pore size should be 1 by 40 mess. And then that means what? Suppose you have this in the sieving plates, and you have here 30 mess and here 40 mess. Am I right? Now when you pass your particle here, it will pass through 30 and retain by 40. So your particle size lies between 30 mess to 40 mess, because it pass through 30 and retain by 40. So that is the 1 by 40 means smaller size. So this is how the industrially how the particle size can be expressed, the 3 by 40 mess. Now this is the approximately equal to 0.71 millimeter average diameter, which we express as dP. Now feed rate, here you are continuously passing the liquid, there is the feed rate, you are passing liquid, this is about 500 milliliter per hour. Am I right? And glucose concentration as 60, so this is operated as 60 degree centigrade, because and the glucose concentration here is about 50 grams per liter. So S0 you can consider 500 gram per liter. Am I right? Now glucose conversion efficiency, that means 60% of glucose should be converted into the fructose here in the product. So so that we can easily find out. And what is the viscosity of the liquid? 3.6 centipoise as 60 degree centigrade, and the feed density is 1.23 gram per liter as 60 degree centigrade, and substrate diffusivity D equal to 0.21 into 10 to the power minus 5 centimeter square per second at 60 degree centigrade, and void fraction is 0.35. Now what do you mean by void fraction? Void fraction means, suppose that this is the particle, am I right? This is the particle that we fix in the column. This is particle, they are lying with each other due to the gravitational force of interaction. When you pass your substrate is the liquid form, it always pass through a void space. Now it cannot penetrate the solid matrix, but whatever the void space is there, it will go like this. Am I right? So liquid is moving only through the void space like this. So that is the void fraction, that is 30% of this solid matrix will be free space. Void fraction means it is considered as the free space, so that where the liquid can travel, free space where the liquid can travel. So that is I have a 0.35. So these are the different parameters that are given. Now let us see how we can solve this. Now for this we will be using one equation, that is Satterfield has suggested the expression for the column height as follows. This scientist, he determined that kind of correlation with the flow characteristics of the fluid with the that size, the height of the column. And during his research work, he find out this is quite applicable for the determining the height of the immobilized column. Now, what he says, that is the z is the height of the column equal to epsilon. Epsilon is what? This is the void space, and R is the Reynolds number. This is the SC is the Smith number, and AB is the ratio of particle surface area to volume, and Y1 and Y2 is called mole fraction of substrate in product. That means Y2 is the mole fraction, because if you have column like this, so you are passing your substrate like this, product like this. So here the mole fraction of the substrate is Y1 and here Y2 and here Y1. So Y1, so this is the input, is this is the feed, is Y1 is the mole fraction of the substrate, and mole fraction of the substrate at the product, that here it is Y2. This is what he has. So this is the correlation that we have. Let us see how we can solve it. Now, first we shall have to find out the Reynolds number. Reynolds number is the what? Du rho by mu, because we know that is the Reynolds number is Re equal to, this is du rho by mu. This is the d is the usually the diameter of the particles, and mu u is the velocity of the liquid, rho is the density, and rho is the density of the liquid, and mu is the viscosity of the liquid. Now, here the V is the here dt by that V into rho by V, where V is the volumetric feed rate. This is the velocity divided the cross sectional area of the column. So, suppose this is the column and we are passing the liquid with a some flow rate, and how we can find out the velocity? Velocity here, velocity is V, they are saying, and V will be equal to what? The flow rate divided by cross sectional area, because what is the cross sectional area of the cylindrical column is the pi r square. Pi r square is the cross sectional area. So, we can find out the velocity. So, this is how we can, volumetric flow rate is this, that but when we do all this calculation, one thing we shall have to remember, the unit. We have seen the different units there, and there that unit, the same units we shall have to. So, that is why the flow rate is given 500 milliliter per hour. This is to be converted into milliliter per second, like this. Now, that cross sectional area of the column, how you can calculate that? The cross sectional area diameter is about 2.5 centimeter. Am I right? So, no, 5 centimeter. Now, if diameter is 5 centimeter, what will be the radius? Radius will be 5 by 2, that is 2.5 centimeter. Am I right? So, this is exactly what he has written, the pi r square. I told you that is the cross section. And so, what will be the velocity? Velocity is equal to that, this is the flow rate 1.138 milliliter per second, and this is the area. Then this will be the centimeter. What is the milliliter? Milliliter means centimeter cubed. Am I right? That, so, this is centimeter squared and this is centimeter. So, your square will calculate, it will be centimeter. So, it is centimeter per second. What is the Reynolds number? Reynolds number that we have given, the d u rho, that by mu, that d is the diameter of the that vessel that we have, and that u is the velocity of the, and this is the density, and this is the viscosity, and this value is coming this. And if you the Smith number, that we get the mu by d into rho. Now, this d is not the diameter, this is the diffusivity, and this diffusivity that has been given in this problem is 0.21 into 10 to the power minus 5. This is the mu is equal to 3.5, this is equal to this, and so Smith number is coming about 1.39 37 into 10 to the power 6. So, this Smith number we can easily calculate. Now, if you then we shall have to find out another parameter, what is the AB. What is AB equal to surface area of the particle divided by volume of the particle. Now, what is the surface area of the particle? This is 4 pi r square, am I right? And this is 4 by 3 pi r cube. This is the volume of the spherical particle. So, this value is coming around 84.5 centimeter per centimeter. Now, and mole fraction, this is how you can calculate mole fraction in case of that this is the column, and here this is the input liquid, am I right? This is the Y1 and this is output is the Y2. The mole fraction of substrate, because we consider all substrate are present there in the form of glucose, so this should be 1. And in the outgoing section 60% is converted, that means how much will remain by this 40. So, mole fraction will be of the substrate will be 0.4. So, now if we have all the data we have and we put the value in this equation, then we will find the height of the column will come around 2.2889 centimeter. So, this is how we can find out the height of the column. We can easily of the immobilized system we can easily find out the. So, in this particular lecture we try to cover some kind of numerical problems, because we first we find out that when you use some kind of cells and that cells undergo respiration, that how much oxygen the uptake by the cells is there, that diffusion problem, and we try to find out whether it is diffusion control. And another we try to find out that in case of enzymatic reaction, whether that is the diffusion control, that we try to find out, and whether it is diffusion control and reaction rate control. And finally, we try to find out that industrially when we apply this immobilized enzyme system, we put the enzyme in a column and continuously we produce product. So, the question comes, for getting a desired amount of substrate conversion, how we can determine the height of the column. So, I try to explain one problem related to that. I hope you understand that, how it related to the flow characteristics of the fluid. We use the Reynolds number and Smith number. With this, try to evaluate the volume of the immobilized column. Thank you very much.